In the previous lecture we started deriving the two dimensional discretized forms of the convection diffusion equation by considering an unsteady problem. The governing equations were the continuity equation and the convection diffusion transport equation, and we defined various variables as jx and jy as shown here in the board, and we first integrated the continuity equation with respect to the control volume chosen, and from that we obtained the following equation: rho p minus rho p naught delta x delta y by delta t plus fe minus fw plus fn minus fs equal to 0, where f, the quantities capital F, represent sort of flow strength across various phases of the control volume. For example, rho u e delta y represents the flow rate through the east phase, rho into u is the flux of mass, that multiplied by delta y into 1, because it is a 2 dimensional problem. So, the third dimension width is 1. So, delta y into 1 is the phase of the corresponding east side of the control volume. So, that represents the flow rate. Similarly, all other terms also represent the flow rate. Now, with this equation in mind, this we call as, let us say, equation 3, we will now discretize the convection diffusion equation. That is equation number 2. So, what we do, we integrate dt dx dy let us put the various limits of integration t to t plus delta t. Remember, we are doing fully time implicit discretization, that will be reflected in the next steps. So, first we integrate the time expression here, and what we can assume? We can assume a piecewise constant profile for both rho and phi over each control volume. So, rho p phi p minus rho p naught phi p naught into delta x into delta y. For evaluating the next terms, first we consider this integral. So, that will become jx at E minus jx at W. Then next what we do, we consider that integrated over y so we have jxe minus jxw into delta y for this particular part of the term. This we call as je minus jw, where what is je? Integral of jx dy or jx into delta y, so to say, at E. Similarly, the same at small w is jw. So, the definition of the j is very similar to a one dimensional problem, except you have the previous j multiplied by a delta y. So, it becomes plus je minus jw into delta y plus here sorry into delta t is there plus jn minus js into delta x into delta t, that is equal to 0. Oh, delta y and delta x are already considered. Okay, very good. So, delta x delta y are already considered in the definitions of j, therefore, you do not have again a repeated consideration of delta x and delta y. So, likewise like je jn, how it is defined? Integral of jy dx at the face n. Now, you can again divide both sides by delta t as you did for the continuity equation. So, the discretized equation will come as this. Let us say this is equation number 4. Equation number 1 and 2 were the continuity and the convection diffusion equation. Equation number 3 is the discretized continuity equation, and equation number 4 is the discretized convection diffusion equation. Now, you can see here that an additional variable density has appeared, rho p. So, you have to eliminate rho p from these two equations. So, how you can do that? You can subtract equation 3 multiplied by phi p from equation 4, then rho p phi p minus rho p phi p. So, phi p will be eliminated. Okay. So, if you do that, you have rho p naught into phi p minus phi p 0 into delta x delta y by delta t, that is the subtraction of the first two terms, plus je minus fe phi p minus jw minus fw phi p plus jn minus fn phi p minus js minus fs phi p equal to 0. So, other than the unsteady term you can see that the other terms have 4 different groups, these are similar ones. So, let us calculate the first group Je minus Fe phi p, that will give us an indication of what will be the discretization of the remaining groups. So, Je minus Fe phi p. Je is integral Jx dy at E. So, rho u phi minus gamma d phi dx minus Fe phi p. Okay. Now, you can non-dimensionalize this one. Remember we are calculating at the small e phase, so appropriate length scale is delta xe. We are calculating at here, this is small e, small w, small s and small n. Now, with that, using that as an appropriate length scale, we can have a diffusion string dE is equal to gamma e by delta xe. If you divide both, both of these terms by dE and multiply by dE, so it will be dE integral of Pe phi e minus d phi dx by delta x e dy minus Fe phi p. See, this is what? This is nothing but the J star. So, in this dE what we can do? So, this part is nothing but the J star, the non-dimensional J, P phi minus d phi by d non-dimensional x. This we defined as J star or a non-dimensional J. Now, what we can do is we can also, so when we have defined d is equal to gamma e by delta x e, that was a one dimensional problem. In a two dimensional problem we can define d in a bit of a different way. This we can multiply by delta y. So, this is the total diffusion strength, because this is like per unit area and delta y into 1 is the area perpendicular to the direction of the propagation of the diffusion flux. So, if we do that, then what we can write it in this way, we can write this as dE into J star at E. That integral of dy, that is delta y, that has been accommodated in this dE term. Okay. So, next what we can write? We can write J star as B phi B of Pe B phi I minus A phi I plus 1. What is I? You are considering the phase small e. So, what is I and what is I plus 1? I is P and I plus 1 is capital E. So, B phi P minus A phi E. Minus Fe phi P. Okay. Remember the argument P is P based on delta xe. You can write B as A plus Peclet number. So, dE A of Pe phi P plus Pe phi P minus A of Pe phi E minus Fe phi P. Now you see, carefully look into this term, dE into P is Fe, Fe into phi p and minus Fe into phi p, these two terms get cancelled. So it becomes dE into APE into phi p minus phi e. So that is equal to small ae into phi p minus phi e, where small ae is dE into capital A, that is the dimensional coefficient, and A of P can be written in terms of A of mod P depending on the scheme you choose. So you can see that it is perfectly generalized. You can select a particular scheme and accordingly substitute the expression of A of P here. Similarly, let us consider one more term, maybe JW minus FW phi p. So let us try to skip a few steps, try to take a lesson from this one and try to write. So instead of dE it will be dW Pw phi w minus d phi dx by delta x w w minus Fw phi p. So this is dW, this is J star at small w. So B Pw phi capital W minus A Pw phi capital P minus Fw phi p. Now you have to eliminate phi Fw phi p here. So now what you can do is, instead of this A you can write this as B minus P. So dW B Pw phi w minus B Pw phi p plus Pw phi p minus Fw phi p, where we have written this A as B minus P. So now dW into Pw is Fw into phi p, that Fw into phi p term gets cancelled out. So you are left with dW into B Pw into phi w minus phi p. It is straightforward to find the remaining two terms which are exactly similar as these two terms. So when you assemble this equation finally, what is the form that you will get? So assemble all the terms, you will get AP phi p is equal to AE phi e plus AW phi w plus AN phi n plus AS phi s plus maybe AP0 phi p0 plus, there is no source term here. So, out of this how can you define what is AE for example? In this particular form, where from it has come? It has come from the multiplier with phi e. What was that? D into A of mod P. So, this is DE into, sorry, not mod P, A of P. So, this is DE, A of P is A of mod P plus max minus PE 0. Right. Similarly, AW dW into B of PW, that is dW into A of mod PW plus max PW 0. Just check the formula for B that we derived in the previous lecture, that will give the corresponding expression of B of P in terms of A of mod P. Similarly, you can write what is AN, just let us write AN and AS quickly. So, AN is DN A of mod Pn plus max minus Pn 0, AS is equal to ds into A of mod Ps plus max Ps 0. Where Pn is Peclet number based on delta Yn, Ps is Peclet number based on delta Ys. So, we have seen a 2-dimensional discretization, and in the 2-dimensional discretization we have generalized it in terms of A of mod P, where the expressions of A of mod P are same as those which we have derived for the 1-dimensional case. Now, so far whatever we have discussed, it has given us a clear idea of the kind of policy or the kind of strategy that we can take to generalize the formulation of a convection diffusion problem. Now, once we have that generalization, the next question is, will the convection diffusion discretization work for all problems? So, we have seen for example that the central difference scheme has certain constraints in terms of its applicability with regard to the cell Peclet number and so on. Now, we will go into a more involved issue concerning the applicability of these particular schemes, or two of these particular schemes so to say, and that issue is known as false diffusion or numerical diffusion. By the name of false diffusion, it is apparent that it is a diffusion which is not a physical one. So, it is an extra diffusion which can be thought of originated as a numerical artifact, that is because of numerical errors or something, or false quantification of additional amount of diffusion is there where that diffusion is physically not there. So, that kind of situation if it arises, then it is told or it is considered that that particular scheme has a problem with false diffusion. Now, how do we address the issue of false diffusion, or what is the correct view, what is the incorrect view? There is a bit of a historical perspective about it, because like when these schemes, when these convection diffusion schemes were developed, remember that the original viewpoint of this false diffusion was not based on the entire sequence of development that was available to the community. So, for the first time when people thought about it was for the first time when people faced a contradiction, when the upwind scheme was thought of as a remedy to some of the problems which the central difference scheme was used to give. So, traditionally the finite difference community was happy with the central difference scheme. Now suddenly after some research people realized that, well, the central difference scheme had its own problems, some of which could be taken care of by the upwind scheme, and that sort of gave a threat to the central differencing community. So when it gave a threat to the central differencing community, the central differencing community tried to assess the upwind scheme on the basis of their own prejudice of the central difference scheme itself, as if that is the standard benchmark, and with respect to that standard benchmark they commented that the upwind scheme is having some false diffusion or artificial diffusion. How they, on what basis they commented? Remember that in the central difference scheme A by D is 1 minus P by 2, central difference scheme. In the upwind scheme A by D is equal to 1 plus max minus P is 0. So when P is greater than 0, central difference scheme gives AE is equal to DE minus FE by 2, and upwind scheme gives AE is equal to DE, right. So this can be written as DE minus FE by 2 plus FE by 2. So if you compare the central difference scheme with the upwind scheme, it might appear as if this DE is augmented by FE by 2 to have the same formula as that of the central difference. So augment DE with DE plus FE by 2, so that this new DE new, so it becomes DE new minus FE by 2, which is same as the formula of the central difference scheme. So if you cast the upwind scheme and the central difference scheme in terms of the same formula, which is not logical, but if you still try to do that, you find that as if you have an enhanced diffusion coefficient in the upwind scheme, which is the original diffusion coefficient plus Fe by 2, and this was originally told as the origin of a numerical artifact in terms of an additional diffusion of Fe by 2. We can clearly understand that this logic has a fallacy, because this logic presumes that the central differencing scheme provides a benchmark formula in which you have to cast all the convection diffusion coefficients, but the central differencing scheme has its own problem. To understand where lies the problem of false diffusion, is it just the choice of the scheme or it is something much beyond the choice of the scheme? Let us try to consider a problem. Let us say that you have two streams of fluid, one with this temperature, uniform temperature profile, that is the upper fluid, and another is another uniform temperature, which is the lower fluid, and these fluids are flowing along positive x direction, and let us say that the diffusion coefficient between these two fluids is 0, that is the effects cannot mix. So if they cannot mix, what will happen? The temperature profile is expected to remain this uniform for the top fluid and this uniform for the bottom fluid. If they were allowed to mix, they would be something like it may be not exactly this, but an effect where you have the temperature of the lower fluid increasing a bit and temperature of the upper fluid decreasing a bit, and they are, so that because they are mixing with each other, but this is not the correct case when diffusion coefficient equal to 0. So when diffusion coefficient equal to 0, this is a predominantly one dimensional problem. So you have AE, consider the central difference scheme, AE is equal to DE minus FE by 2, AW is equal to DW plus FW by 2. Okay. So when the diffusion coefficient is 0, these terms are not there. So AP is equal to AE plus AW, that is FW minus FE by 2, and this is equal to 0 by continuity. That means phi p cannot be obtained, because to get phi p you have to divide the right hand side by AP. So it is a division by 0 problem. So you are trying to assess the physical situation by considering a scheme as a standard which itself does not work at 0 diffusion strength. On the other hand, if you consider the upwind scheme, you have phi at small e is equal to phi p if Fe is greater than 0. So at all the upstream points you have the same value of phi, the diffusion term will be 0, because the right hand side is the diffusion term which is 0. So it is purely on the basis of advection. Remember, in the upwind scheme, in the left hand side you have the advection term represented by upwind, and in the right hand side diffusion term represented by the central difference scheme. So here, because the diffusion coefficient is 0, right hand side is there no more, so only the advection term is the dominating term, is the influencing term, only that term. So phi is equal to phi p if Fe is greater than 0, that means all the subsequent stations will have the same temperature along x. So this profile will not be disturbed. Okay. So whatever is the change, this type of change is not possible, because this profile will remain intact and the solution will be there. So in the limit, as diffusion strength tends to 0, the upwind scheme does not work, the central difference scheme does not work, but the upwind scheme gives a corresponding physically consistent solution. Still there might be a problem with false diffusion, but that problem can be assessed by aligning the flow in a different orientation. Let us try to do that. Now let us say that we are considering the same problem, but the flow is now inclined at an angle 45 degree with the x axis. So it is an inclined flow like this. Instead of flow along x axis, it is 45 degree with respect to the x axis. And let us consider a problem domain like this. Let us say that on one side of this flow direction you have the temperatures as 0 degree centigrade, 0 0 0, and on other side it is 100. So these were the boundary conditions. On one side, on the side below it is 0, on other side, the side above it, if you just consider this as below and this as above, on other side it is 100. So let us try to calculate the values of temperature at the other grid points, assuming that the diffusion coefficient is 0. So, the same problem what we have done, we have now oriented the flow in a manner inclined to the grid orientation, that is the only change that we have made. Now, let us consider the grid layout. This is the point P, E, W, N, S. The flow is coming in this way. So, what will be the corresponding coefficients, which if you use the upwind scheme, out of these 4 W, E, N, S, which two will be effective? W and S, right, because those represent the upstream directions. If you resolve this flow into components, let us say that this is rho V, this angle is 45 degree. So, this is rho theta equal to 45 degree. So, this is rho V cos 45 degree, and this is rho V sin 45 degree. So, with respect to this flow, this is the upstream grid point, with respect to this flow, this is the upstream grid point. So, you have AE equal to 0, AN equal to 0, because cos 45 degree and sin 45 degree are the same, you have AE equal to AW. Okay. Sorry, AS equal to AW. Remember, we are using the upwind scheme. Instead of using the formula, we are directly using the concept of the upwind scheme to do it quickly. Then AP is equal to AE plus AW plus AS plus AN, consider a steady state problem. So, AE, AW and AN are 0. So, this is 2 AW, and your governing equation, discretized equation, is AP phi P is equal to AW phi W plus AS phi S, other terms are 0. So, 2 AW phi P is equal to AW phi W plus AW phi S, all these are all AW. So, phi P is equal to phi W plus phi S by 2. So, let us see what is the implication. Implication is very interesting. So, this is like W, this is like S. So, this point will be 100 plus 0 by 2. So, this is 50. This is 50, this is 100. So, this will be 75, right, 100 plus 50 by 2. Then this is 100 plus 75, 175 by 2, what it is? 87.5. So, you can see that what you expected that on one side of the diagonal temperature will remain as 100, on other side it will remain as 0, because there is no diffusion across it, but that is violated. Now, you are having a false diffusion, because of which there is a gradient in temperature in this side. The same problem could be avoided if your x axis was oriented along this, just like this case. Actually, it is a camouflage, it is the same problem, only the axis is misoriented. Physical problem is the same, that is, you have one line, on one side there is a temperature, on another side there is another temperature, and there is 0 diffusion across that. Here we have just inclined the problem, nothing else. So, what you can see here is that now you have a false diffusion. So, what we can infer out of this, that there is a false diffusion which can be attributed to what? Which can be attributed not to the particular scheme as such, but the misorientation of the grid lines with the flow direction. So, this angle theta is the contributor to to the false diffusion. So that is the correct viewpoint of the false diffusion. It is not so much on the scheme, of course the scheme has some role to play and one can try to improve upon that, but more importantly it is the orientation of the dominant flow direction with the grid lines. If that is misoriented, that can give rise to these problems, and in fact one can calculate a false diffusion coefficient. I will not go into the details of that, but just will just give you an expression. So it can be shown that you can have a corresponding expression for the false diffusion. Our objective here is not to prove it, but to see that what we can get from this expression. In this particular expression, so this is an expression for a false diffusion coefficient, gamma is a diffusion coefficient. So this is not a correct diffusion coefficient but a numerical artifact just like this, and we can see that it is a function of this angle theta. So it is maximum when sin 2 theta is 1, that is theta equal to 45 degree. So when the flow is oriented in a bad manner, that is it is misaligned with x, misaligned with y and maximum misaligned with the combination. So intuitively that is theta equal to 45 degree, where the misalignment with both of these is sort of equal, and you can of course minimize the false diffusion coefficient by reducing the grid spacing delta x, delta y, these types of things. So this formula gives us a clue. It is not important for us to remember the formula. What is important for us is to understand that the false diffusion is governed by this angle theta, which is very important. So if you make this angle theta equal to 0, the false diffusion coefficient is gone, that is when the flow is oriented along the grid lines. Okay. Now what can you do to minimize the false diffusion effect, considering that the flow orientation is something which is not in your hand. Of course if you know the predominant flow direction, you can orient your grid choice accordingly, but in a complex problem you do not have a single predominant flow direction, and it is very difficult therefore to orient the grid lines in a particular way which will minimize the false diffusion. So what is the way out? The way out may be to have some other types of differencing schemes which are a bit more, I would say bit less prone to false diffusion than the upwind scheme itself. So you can tackle it by considering the improvement of the scheme or the grid layout in a way that it is oriented in a manner which is oriented in the direction of the flow. Now predominant direction of the flow is very difficult to get in complex problems, so we try to go for an improved scheme, and that one such scheme we will give an example, that is called as quick scheme. So its full form is quadratic upstream interpolation scheme for convective kinetics. That is the full form of the quick scheme. So what it tries to do, if you have a grid point I minus 1 and a grid point I, and this is the interface where you are interested to calculate the flux, then what it takes is, if this is the flow direction, it considers a quadratic interpolation, that is a quadratic profile assumption, instead of a linear profile assumption, a quadratic profile assumption. So a linear profile assumption required how many points? 2 grid points, quadratic will require 3 grid points. So another grid point I minus 2 located upstream, so at the interface 2 grid points at the upstream end and 1 grid point at the downstream end, so that the scheme is capable of considering not just the upstream grid point effect but also the downstream grid point effect. So, it can be thought of as a sort of improvisation of the upwinding scheme or a higher order upwinding scheme, so to say. Now, let us say that this distance is delta by 2, this is delta by 2 and this is delta. Let us fix up our origin of the coordinate system somewhere, let us say this is x equal to 0 and let us say that we consider phi as a0 plus a1x plus a2x square. This is a quadratic profile. So, our objective will be to find out a0, a1, a2 in terms of phi I minus 2, phi I minus 1 and phi I. So, you have at x equal to 0 phi equal to phi I minus 1, at x equal to delta phi equal to phi I and at x equal to minus delta phi equal to phi I minus 2. So, from here we can write a0 is equal to phi I minus 1. Then from here we can write a0 plus a1 delta plus a2 delta square is equal to phi I. From here we can write a0 minus a1 delta plus a2 delta square is equal to phi I minus 2. Let us say this is 1, this is 2, this is 3. Now, you can subtract, so 2 minus 3, then you will have 2 a1 delta is equal to phi I minus phi I minus 2. So, a1 is phi I minus phi I minus 2 by 2 delta and you can add 2 and 3. 2a0 plus 2a2 delta square is equal to phi I plus phi I minus 2. So, a2 will be phi I plus phi I minus 2, minus 2a0 means minus 2 phi I minus 1 by 2 delta square. So, what you require? You require phi at the interface, that is after the interpolation you require. So, what is phi at the interface? That is phi at x equal to delta by 2. So, that is a0 plus a1 delta by 2 plus a2 delta square by 4. So, that is phi I minus 1 plus a1 delta by 2. So, plus phi I minus phi I minus 2 by 2 delta into delta by 2 plus phi I plus phi I minus 2 minus 2 phi I minus 1 by 2 delta square into delta square by 4. So, this delta square and delta will cancel. So, it will be 8 in the denominator. So, how many phi i's are there? You have here you have, if you take 8 then this is 4 into 2. So, 2 phi I then plus 1 phi I, 3 phi I, then phi I minus 1, here you have 8 minus 2. So, 6 plus 6 phi I minus 1 and phi I minus 2, here you have minus 2 and then you have plus 1. So, minus 1. Okay. You can see that ultimately it is a weighted combination of I minus 1 and I minus 2. Sum total of the weight 3 plus 6 minus 1 is equal to 8. Okay. So now based on this consideration let us try to write a discretization. So P E W, let us consider a one dimensional problem and let us say that this is the flow direction. Okay. So if this is the flow direction, now let us write the corresponding discretized equation. So you have rho u phi d dx of rho u phi minus gamma d phi dx equal to 0. So if you integrate it with respect to x, rho u phi at E minus rho u phi at W is equal to gamma d phi dx at E minus gamma d phi dx at W. So you require phi at small e. Remember rho into u equal to f. So the first term is f e into phi at small e. So with respect to small e, I is p, sorry, I minus 1 is p, I is e and I minus 2 is w. So 3 phi e plus 6 phi p minus phi w by 8, okay, minus, now you require phi small w. So you require another upstream point. So that conventionally is given a name WW. So it is another upstream point just equidistant. So then you have f small w into now 3 phi p plus 6 phi w minus phi ww by 8. So this is the advection term profile. The diffusion term profile you can still take the piecewise linear profile, because the whole problem was associated with the representation of the advection term. So diffusion term you can write d into phi e minus phi p minus dw into phi p minus phi w. Where d is gamma e by delta x e and dw is gamma w by delta x w. So remember one very important assumption is that quadratic profile for the advection term and piecewise linear profile for the diffusion term. So not the same profile for the advection and the diffusion term. So if you now assemble these terms, you will get an equation of the form AP phi p is equal to AE phi e plus AW phi w plus AWW phi WW. There is no B here. So what is AE? DE. So if you consider the right hand side here, so DE minus 3 FE by 8. What is AW? DW plus FE by 8 then plus 6 FW by 8 AWW is equal to minus 8 Fw by 8 and so on. So, you can clearly see immediately that this scheme has a problem, that all coefficients will not always be of the same sign. So, if you have dW, Fe and Fw all positive, which we have considered in this problem, then only Aw is guaranteed to be positive, neither Ae nor Aww is guaranteed to be positive. It depends on the relative advection and diffusion strength, relative Fe and De, and Aww is always negative. Only Fw by 8, okay, that is fine. So, we can see that this particular scheme tried to rectify a problem, but has created a different problem. So, it is like having a medicine where the medicine is trying to take care of a disease, but having another side effect. So, the disease is a false diffusion, it tried to take care of the false diffusion, but in the way it incurred a possibility of having all coefficients not of the same sign, and that could give rise to physically inconsistent solutions. So, we can summarize that it is not trivial to choose a particular scheme, perhaps choosing a simple scheme is better, and once one chooses a simple scheme, it is important to take care of the fact that you satisfy the basic rules which are corresponding to a correct action of the discretized equation. So, we stop with the convection diffusion equations here, and from the next class we will start discussing on how to solve the fluid flow problems or the Navier-Stokes equation, because till now we have solved the convection diffusion equation by assuming the flow field is known, but where from the flow field is known, it has to be solved from the fluid flow equations, that is the coupled continuity and the momentum equation, that we will take up in the next lecture. Thank you.